speed a little bit. Charlotte, other thought that helps coordinate.
Hi, Jose. It's great. It's great to meet you.
Hi, nice meeting you.
And I really look forward to your.
Thank you.
presentation
Thank you.
today.
We'll see how it goes.
This would be way up higher.
Yeah.
Cannot see my. Just, I cannot get to,
Maybe you have to press got it,
yeah, but
but you can't get there. Oh. I also have if it helps, I have a laser pointer. if you want.
yeah, no, we're
No, you
good.
don't want that,
I
right?
think,
What?
I think so.
Oh, shoot.
Thank you. We weren't sure what it's- Well, not that it's technical. Oh, because they were so busy following. Sure. That's one of the problems is that like. Semester.
I'm Luis Sacarino. We have a meeting a little bit later.
How are you?
Very good. Excited. Nice to meet you. Excited to.
Where are you from?
I'm from Peru. How are you?
Okay.
Ciudad de México. Okay, I'm from Lima. Very good. Yeah. How long have you been here?
In the States?
Yeah, yeah. Oh, in the States or in the
25 years.
Okay.
He's asking.
Experience, yeah, 20 years.
Oh, wow. You? Well, not in this area for years, but before I was in the.
What do you?
I work on disaster risk and all. So I'm more like a structural. So my group is calling us. Okay, ready.
Yeah, I didn't know.
Yeah, it's kind of over the outside, like what it's. Really sometimes like to also. I feel like the coffee is so here, but I don't know what it is. They kind of, they all blend together. Oh, I guess it's just really good. different groups. Then we just have operations that are they're completely separate from the environment.
Do it first.
That is seeing from
Base.
Luis, do you still have more people coming?
I forgot what one. I'm not sure. And I've seen.
Okay, should we wait a few more minutes or should we get started?
Oh,
Okay, a couple of minutes. Wait a couple of minutes.
Okay.
no worries.
We also have like, us, they collaborate. with some- Symbiosis and is like their math and science, so.
Well, I think not.
And.
Oh,
Yeah. For instance.
You're going away.
Right.
And then.
No.
Meta. Entourage.
It'll get it.
That's fine.
I don't think I need a break right now. So. We can talk this.
My color visor is. I don't know.
What's that?
Wait, you're pointing, where are you pointing? In Brooklyn? No, it's in. Like across. Anyone you talk.
Yeah.
And then last rehabilitation. I guess we'll go ahead and get started. Okay, so I'll quickly introduce our speaker today. We're very honored to have Dr. Jose Ramirez Marcus with us today from Stevens Institute of Technology, where he's a professor in the School of Systems and Enterprises. He is the director of the Enterprise Science and Engineering Division. He's a former Fulbright scholar. He received his PhD and master's in industrial engineering from Rutgers University. And he also has another master's in statistics from Rutgers University, as well as a degree in actuarial science from the Universidad Nacional Autónoma de México. His research efforts are developing models for system operational effectiveness, and in particular for system resilience and disaster resilience. And he also develops methods for using tools drawn from evolutionary computation to optimize system performance and design. And he has published over 100 refereed manuscripts, wow, in technical journals, book chapters, and industry reports. So with that, I will hand it over.
Thanks, Jackie. Thanks for the invitation. Thank you. We'll see if you clap once I'm done. Yeah, so it says beyond system resilience, new approaches to understand symbiosis between systems and communities in times of disruption. And there's a caveat there also in times of no disruption. So we focus a lot on disruption and in the word resilience. So I wish that we could move a little bit from this concept of resilience that we've been looking at it for a long time now. So let me give you the first part of my talk is going to be kind of us getting to learn the language and have a similar language so that I clarify clearly what I understand by resilience. And after that, I'll talk about some of the projects that I've worked on resilience. So more than a single research talk, it's going to be kind of a journey along the areas of resilience that I talk. And so I'm at Stevens, and so just across the river, and you can see my office somewhere around here. We used to have a lot of collaboration with NYU. I was talking with Jackie before the start of the talk. Anyway, resilience. So I just quickly went and web searched resilience, and so it says here the capacity to recover quickly from difficulties and toughness. If you can read over there, it says remarkable resilience of British institutions. So that's strange. The ability of a substance or object to spring back into shape, elasticity, and then you got all these different synonyms over there that from an engineering perspective makes it difficult to really square and define what resilience is about. And so, by the way, this is how much has been written and discussed about resilience in the engineering area for the last years, and you can see a significant explosion of research related to this topic. Anyway, and here you go, a little bit of more introduction of where we are in terms of resilience. So everyone talks about, every single area talks about resilience. You can go from psychology to the environmental sciences, neuroscience, over there, small node engineering, right? And so this makes it difficult to have a clear understanding among different areas, especially if you want to have some collaboration, just understanding what it is. So my work on this starts a long time ago in 2009. My background, and I'll talk about this in a second, is on reliability engineering. And so I did a lot of work on network reliability, trying to understand how networks in its most simple form work or fail. The caveat is that most networks are not binary and they're really multi-state. And so that was my area of research. And then around 2009 or before, I started hearing this concept of resilience of systems. And so I started working on this, and what I developed was this concept in terms of system that is related to the work that I did before in reliability. And so more than having a single metric of resilience, in these engineering terms, I understand resilience as the whole process of a system. And what you have here is a schematic of that process, and you might have a system, whatever that system is, and this is defined as that block at state S0, which would be an original system state. Under reliability terms, you have this system that in its steady state behavior can experience failures during T0 to TE, but these are intrinsic to the design of the system, right? And so you can think about a computer. A computer has some specific behavior, and you don't want it to fail, right? You want it to have a reliable behavior. And so that part relates to what I describe as reliability, the reliability context. When there's external forces that affect the system with a disruptive event, in this case, it's disruptive event EH at some time TE, that system might experience a reduction in its performance. And so it's very important that unit or that function of performance is well identified. In this case, it's defined as F of T. Reality it should be phi of T, but anyway. So there's these systems that have some performance, and that performance needs to be clearly defined, right? Because when there's a disruptive event, that performance will suffer and it will degrade. In this case, the degradation is decreasing, but you can think about degradation that it's increasing, right? And so an increasing degradation would be the case of delay, right? And so there's a disruption in a system, and that degradation function starts increasing, and it's a negative behavior. And so that part, we call it survivability or vulnerability. It tells you how survivable your system is to these disruptive events, or how vulnerable it is to these disruptive events. That has also a lifetime or a time of effect. At some point in time, that disruption effect will stop in your system, and there's going to be a time where that disruptive event stays or maintains itself until there's some recovery action, and that recovery starts performing, right? And so once that recovery action starts, it takes some time until we call it here TF, where the system state is recovered. That system state might be an original, it might be lower, it might be higher. In this case, it's just an one instantiation of that potential schematic, and in this case, the system state is below its original. And so we can define now, based on this performance function, based on the disruptive event, and based on these different timelines, resiliency at time TR, and that TR is somewhere in the bound of TS and TF, right, as a ratio. And this ratio is just, here is the loss over what is being recovered. And so if we understand resilience as a loss recovery as a function of time, that's what resilience is, and that's how we could start measuring, right? And so you can think about disruption here in the transit system, right? And so now my time, my trips are getting longer. I have to recover that segment of some transit system, and within that time, I'm gaining again my original time. And so that's recovery over loss. And so based on that, and I'm not the first one to discuss this, there's been a lot of models described for resilience. Here's another one that talks about the resilient triangle, very similar description, just that instead of describing this formulation as a time-dependent function, what they want to obtain is that integral in the triangle or geometric figure that generates between points A and B, but you can see that there's also time. So it's very important that we include time in resilience. And again, it's a process that involves these different points in time, and it's not a single case of metric, right? Here's another resilience triangle that describes time, and it includes this concept of robustness and rapidity. And so obviously, most of them are interrelated. So rapidity, so how long it takes you to recover, that affects obviously your resilience. How robust is your system? In other words, how well it can take disruption, obviously, also affect how well you take into account or how short that resilience process is. Okay, so I'll be working with this concept in mind. You can decide whichever you want of those three, but that's the concept. So once we have discussed this concept, we can start talking about, okay, so which systems experience resilience, right? And so first of all, there's those that experience reliability, right? And so when I talk about a cell phone, well, my cell phone is not resilient. My cell phone should be reliable, right? I don't want it to fail, but when it fails, I'll send it to repair and it will come back repaired. In other words, it will be maintained. It's very unlikely that there's going to be an external disruptive event that will make my system become resilient, right? An airplane shouldn't be resilient, should be reliable, right? I don't want to talk about resiliency in an airplane because that means that there's serious issues during my flight, right? I don't want that happening. I want to be able reliably get from one place to another in my airplane, right? Unless, of course, there's caveats here, right? Oh, there can be the airplane lost one engine and all of a sudden you can get another plane to bring the passengers. That would be a resilient process, but pretty unlikely that that will happen. And so very important that we identify which systems are experiencing resilience so that we don't misidentify them and try to do something that it's really more related to reliability. Now, the part of survivability, well, I want the airplane to be survivable, right? If there's a disruptive event. So, and the example that I'll give is, well, within the design, there's this case where you can have lightning hitting your structure, and that's within the design. So you want that design to be survivable, right? And so, for some cases, we want the system to be reliable and we want the system to be survivable to some events, right? And so that this decay, when there's that disruptive event, which might not be considered within the design, should be as small as possible, right? So there's an example of that on disruption, right? And so here's electrical. This is work that I did a couple of years ago. It's in risk analysis. It's about identifying the economic impact of electric outages in commercial areas in New York City. And so there's no resiliency here. There's just survivability and impact, right? And so how is this done? Well, you look at the impacts of different disruptions in the network topology. And so what you're seeing here on top is a network topology with different nodes representing stations, and the arc are the arcs within those stations. The red node over there describes the node that it's failed. The green nodes and blue nodes are working, green nodes are affected. And so from there you can see based on, so I work with this with a colleague, an economist. And so that economic impact, it's an index that can be extracted from the lack or reduced energy that might affect these different sections in New York City. And so based on that, you can create a profile of effects from the energy network to the economic areas, and this is what it would look like. So what can you do with this? And so the idea is that, oh, well, if I know the impact of these different events, I can start protecting or identifying resources that might allow me to reduce this level of impact. So that would be a hardening of the system, which is one part of the resilience part, but we wouldn't talk about the system being resilient. So we would talk about the system being hardened. Okay, and so finally, which systems experience resilience? And so what I mention or what I posit is that, well, there's gotta be a recoverability part in there. And so the subway system is a system that experiences resilience because there might be a disruption. Our performance function is clear, right? It's delay, right? It's number of passengers, right? And so any disruptions might affect this type of system. And so once you have the disruption, you can look at the system level and see how that performance function is affected and what restorations you need to do. Same with air transportation. And so here's, I'll talk about framework applications, but just quickly, here's a simulation study that we did to try to replicate the effect of disruptions in 42nd Street. I don't know if you were here or if you remember, but there was a bomb in the solo bomb where on 42nd Street a couple of years ago. Anyway, so we wanted to replicate that that disruption, a man-made disruption, on the intertransportation when we consider both subway and transit in terms of MTA buses, right? And so what you are seeing here is the increasing delay once the event happens and how that is changed. There's obviously two cases. One is the bus stop on 42nd Street, and the other one is the subway station. I'll talk about some other applications as we go. Okay, so there's one caveat in all of these models, that they generally assume one single event. And so if you look at material resilience, well, that's not really the case. In material resilience, what you have is really a profile of the material for a number of events, in other words, forces, right? And so what you have is really a description of the stress within a material, and for that you profile the resilience of the material. So this is really what I'm trying to do in this area. So why is that important? Because I want to profile a system, right? Its stress profile, and then see how it bounces back or behaves throughout all this process. And so where we are now is just in that case, one stress, see the effect and report the effect in terms of this resilience process. So that's what we want to do, is then have a system where we can actually look at a multitude of stresses through time and profile its resilience. And so here's the 2D visualization with time on the x-axis, time on the y-axis, stress on the x-axis, and the profile of resilience as a function of color. So this is really a 3D. This is how it will look in 3D. Why am I interested? Well, now we can do two things. So one, we can compare different systems and talk about which of these systems are more resilient, assuming that the stress profile is the same. Or we can look at different hardening and restoration approaches to identify for a single system which one is the best, right? And so here you start looking at concepts of optimization, right? And so let me just go back. And so this is just a toy network, a laboratory network. And so what you have here is the profile based on two different hardening restoration approaches. And so so you need a little bit of comparison here, right? And so the stress here is looked at in terms of component failure. And so there's plenty of different stress profile that you can look at. So if it's force, it might be superstorm. It can be 1 in a year, 1 in 100 years flooding. If you're looking at a water event, it can be a 1 in 100 years earthquake. Whatever that implementation might be. What I've been trying to do is be event agnostic and just having the stress related to the disruption of the components in the system. And so the idea is, okay, if you have a stress level of 1, that means a stress level of failing 1 component. If you have a stress level of 2, that would be 2 component failures. There's some limitation to this problem because as your system grows, your computational ability to do this is significantly reduced. So here comes a statistical problem that I'll talk about in a second. Okay. For this case, since it's a small case, we can actually look at the different effects that these different stresses have. And so now we have this profile for the 2 resilience processes of these 2 cases of hardening and restoration. And so which one is better? And so that's another problem. And so this is a problem of stochasticity. So which distribution is better, right? And so just visually, I would say that if you're looking at it, the right hand side profile has much better resilience profile than the left hand side, and this is just because of the amount of blue that you're seeing there. But there's one case where the system stays completely down, right? And so again, the idea of having these different stressors is that now I can profile my whole system, and I can say without depending on the event, which system is more resilient. Yes.
Why are the red balls or lower levels being pushed over time further away?
So the choice of time in the y-axis here is so that you see the rebound, right? And so the red case over there, so in stress 8 on that second graph signifies that at time 60 the system was still in its worst case, so there was no rebound, right? And so if you imagine it in this way, that would be the line that is only red in the upper part. And so there's the restoration or the hardening are not really doing anything to the system, right? In this case, number 8, right? Makes sense? Did I answer your question?
Yes.
All right. Okay, so most of this work and what I've talked about right now is related to the infrastructure system, right? And so here's a power network. Here's how it can fail. Here's how you can restore it. Here's a transportation infrastructure. Here's some events that are occurring that are disruptive. Here's how it can be restored. There's one big part that it's not being considered, and that is the user. And in this case, the user for all of this infrastructure is a citizen, right? And so the citizen or the person is actually using these systems. And so depending on their usage and how they use it, they might affect the behavior of the system. Depending on how the system is structured and designed, they might affect the behavior of the citizen. And so what I've been doing for the last 5 years is trying to understand how people behave within these systems and how the systems generate behavior. And so the next part of the talk is about people. And so just like I want to create this concept of system resilience, I want to create a concept or a useful way to measure community resilience. What's out there, first of all? And so most of what's out there is these indices that are really qualitative about what a resilient community should look like or should behave. And so given that my background is in math and my PhD is in engineering and I have a statistical that I need something that it's more quantitative than this checklist, but it's very elusive, right? And so what is it that we want? Well, this similar concept in community, but that we can characterize, right? So what do we mean by a community in its performance in its stable state? What are the disruptions to this community? How the community performance, whatever that is, reduces, and how can we bring it back, or how is it brought back? And there are many examples of this. And so whenever disaster hits, community comes together, right? And it's community that brings back the system together. And so here are some examples. So earthquakes, right? And so whenever there's an earthquake, at least in Mexico, the community comes in and works very hard so that the system is restored as soon as possible. Not only that, we've learned a lot from previous of these events. So now there's the hardening part to reduce the effect on the community. And what's that hardening? So I spent early 2022 doing a sabbatical in Tec de Monterrey in Mexico City. And one of the days that I was there, there were these alarms sounding early in the morning in my apartment, and I didn't know what was going on. So I looked out the window and everyone was outside and they were telling me, come out, come out. And it's this new alarm that they have that I think it's 1 minute before the earthquake hits Mexico City, there's this alarm sounding. And so that is kind of hardening the system so that the community is more survivable, right? And so when we talk about that performance function would be injured or accidents within the community. All right. And so since I've been trying to understand behavior, there's two ways to actually do this. And so in the case of an event, I need to talk to people, right, and survey them. Or I need to somehow have some way to understand what people are experiencing during these events that I'm interested in. And so what we have done is we decided to do this electronically, right? So I want to extract information, as much information as possible. And so we started looking at NLP. And so natural language processing, so that I could understand from vast amounts of data, trying to understand behavior of people during events. And so what you'll see is 4 different things that we've been doing, and now events and community become a little bit fuzzy. And so what's a community? And so what we are describing in this case as a community is a set of people that are related to an event, right? And so for our first case, we have this concept of galaxy and star. And so what you're seeing here is social media based. And so, and in this case, specific Twitter, but it can be done as long as the process that we implemented to create these visuals that you're seeing is satisfied. And so what you're seeing is here two visuals. The blue visual describes a star, and this star is a tweet, and that tweet generates some kind of responses, and the responses generate other responses and so on. And so it creates what we call a star. That star, if you follow through some time, there's other stars. And so we can create this concept of galaxy, and the galaxy is just a set of stars, right? And so for that event that we're looking at, in this case, is Bernie Sanders was looking at, we looked at what he was talking about in 3 weeks, starting from mid-February 2019. Why? Because we were interested in this disruptive event, which is not really disruptive, but it's the process of electing a president, right? And so we wanted to see what was going on with the discussion among different actors and seeing how that discussion was resilient or not, or if it had some caveats. Okay, and so what we can do now is this topic aware stars. This is for one case, so we can identify topics. We can look at which topics are important, and within those topics, we can look at how galaxies are changing. And now we go from a galaxy to a topic-aware galaxy, where I can understand what people in this specific case are talking about. Why am I interested in that? Well, because I might be interested in using or in asking citizens to be sensors, right? And so this citizen and sensors, right? Here's the Sandy tweet galaxy. There's 2 specifics, but what do I want to do? I want to identify these tweets that for me are important, that allow me to identify some important aspects of the event. Because at the end, what I want to do is I want to create some type of rule-based guideline or guidelines to what? To either harden the system during disruptive events, or to restore the system to its original state, the faster the better, right? And so what we're really looking at is this process of data from citizens during event, extracting some topics and discussion, and creating some type of policy with government as the leader, right? So here are those policy suggestions. There's by the way, every every of these slides is a paper that I could easily share with you. Okay, so that would be in the sense of people and events. During the pandemic, there were a lot of product disruptions, and so another area that relates to this is, well, so how are companies' reputation being looked at based on their disruptions? And so and this can be extended to other more socially conscious areas, but what we have done is we've created based on again, so this is more or less the process that we create. So we extract data from one of these social media companies. It doesn't have to be Twitter or Facebook anymore. It can be Reddit, or it can be any potential place for online discussion. There's some type of text analysis, and then there's this, in this case, there's this visual analytics. This is a quality control table that we created to actually follow how disruptions in social media can affect the reputation, and here reputation is related to the stock of a company. And so here's the example of Samsung Galaxy 8. You remember where it exploded, and so that's for Toyota and how it looks like. Anyway, the last one before I open or I close the talk and open for discussion. So I mentioned that we also use or try to include the citizen as a sensor. And so how is the citizen involved here? So this is work that we did on Metro North, and this describes the number of records in terms of, so people would text about the service real time. So we got that information, and what it says is here a little bit of description of what they what this text would look like. And similar, Metro North has a system that text delays, and so we wanted to compare what citizens were describing versus what Metro North was presenting. And so this is related to quality of experience, right? And so a lot of systems, people are interested in the system performing based on very specific metrics, but the quality of experience is rarely taking front row. And so here's what here are very different activities. And so what you see in gray in each one of these graphs is the Metro North response versus the citizen as sensor response. And so this would be a delay, each of those, and it would be described as significantly higher by each of them. And so with that, I'll stop and open to any questions if you have. Thank you very much. Yes.
Thank you so much for this really comprehensive presentation. I was curious about when going to the community level and trying to understand all these phenomena. Could you comment a little bit on the computational struggles that we may have? I think at some point there was a mention of using optimization. I understand these types of methods may not scale. So what's your experience when trying to do, say, for a big city like New York City, an analysis at the community level?
So I've worked in many proposals with in New York City, and so the main problem with the community is understanding what community, right? Because there's many communities within the city, right? And so first of all, defining that. So I never talk about a definition of community, right? So that's one drawback that this work has. The community here is in most of these cases is an online community. So the first critique that I usually get is, well, this is not entirely encompassing, right? Because there's people that just don't go into the cyberspace, and so I'm not really taking it. So the second part is that these techniques should be used in line with traditional surveying, right? And so because that gives you a lot of information. So that's the first one. Mathematically, I never talked about that that concept of resilience within the community. We can see the different resilience. For example, the galaxy for Sandy, we can see how the galaxy is dying, right? And so that's good for us because that means that, well, at least that seems to be good because there's no more discussion about the effects of Sandy, right? But I'm not intrinsically identifying the performance function of the community. So that's a struggle, right? That's the best I can do at this point. So we use these galaxies as a proxy for the performance of the community, and the performance function here is the density of that galaxy, right? And so how dense it is, that's great, right? Yes.
In the first part of your presentation, you show models, right? Network models that you can assess or inquire disruptions and what happens, how they propagate to resiliency. And the second part is more like people and how you monitor the social media. Have you thought of ways to connect the two of them? Maybe like social media in data, or I don't know, aggregated models of the first part.
So yes, there's two ways. So in fact, we've done work on how social media might affect power consumption. Right? And so, and again, this is in a laboratory setting. And so what we would take is an IIE network, and we would take a social network and say, okay, these nodes interact. Given that there's a disruption or an event in the social network, this might lead to higher consumption of energy in the energy network, and these would be the problems, right? So that would be one where this might come together.
Why higher consumption of social media?
Excuse me?
You mean that there is higher consumption?
No, there's higher consumption in the power network, right? Yeah. So one might say, oh well, they're going to increase the cost of gas in the next 20 hours. Use as much as you can. Right? I mean, I'm just giving you an example. The second one is using actually the social media experiment, as I was saying, the galaxy as a proxy of the system, right? So the galaxy becomes your system. And so changes in the galaxy can be modeled based on those first models that I described. And so you might say, okay, so what is changing the behavior of these galaxy or the size, right? Any other questions? Yes.
For this type of system, do we need to know the exact attack or disruption model? Or do we only look at the performance measures?
So you need to identify the performance measure, right? Because no performance measure, then it's there's no resiliency process, right? I would like that most of it would be agnostic to the event, but you might say, well, I might want to. So for Sandy, it was clear what we were looking at. I mean, because that was a big event that we wanted to look at and see how it behaved pre-Sandy, during Sandy, and post-Sandy. Yeah.
For the natural language processing model that you showed, is there any possibility of introduction of biasness where the data is coming from?
So I get this question a lot about fake news and fake and bots, right? So what turns out is that so very unlikely that these are going to be bots, the big ones. So the bots are in the, so you can see that there's a lot of noise, right? And so some of those noise is generated by this type of accounts, or because of the number of the size of these galaxies, it's very unlikely that you will go into those stars and see that they're biased, right? And so we have created yet another step that talks about coherency within the discussion happening in the galaxy. And so if you say something incoherent related to that topic, then you're tagged as being incoherent. So that's some ways that we try to manage this issue.
And one more question, like during a disruptive event such as flood or anything else.
Excuse me?
Disruptive events, just floods. If we try to use these models for like emergency response, try to see where there is more disruption. But like people in the most disrupted areas are not able to even use social media.
So yeah, so that's why I started with saying, so some of it has to be really tackled together with traditional surveying, right? And so so the idea here is to follow this process that leads me to some guidelines that can be acted upon, right? If you're doing this live and creating this type of galaxies real time, right? So every day I go and look at it, and every day I look at it and see how it's evolving and what is changing, then this could happen that, well, some parts are not being clearly identified, but then we can get into concepts of geolocation and so on, and then some techniques to identify these areas that are not being looked into. Okay. Yes.
So interested, this graph here on the right, can you explain what we're looking at here? Right, so beautiful, that graph.
Which one, the galaxy or the stars?
Not the one on the right. So
A and B, the one that has A and B. Okay, so this is similar to this concept of a star. It's just arranged in a different way, and so what you're seeing here is two tweets, and so and there's sentiment in that tweet, and so you got A. There's a tweet. It's probably about some event that happened. Probably one of these. I don't know. Maybe it's about bringing food to the church, and so it's a positive tweet. And people are commenting on that tweet, and so that's what you see on the first on the first part of the start. There's a second level that responds to the tweets of the first tweet, and there's also sentiment. But now you're seeing that there's some cases where there's red sentiment. So probably someone said something that was not nice, and that's how it's described. And then each level is a response to the response. And so that's what you're seeing on A. On B, it's another tweet. And the color is even more blue, so it's more positive and so on. It's two separate, so it's those two stars that are arranged in a different way.
It was a wonderful talk.
Thank you. All right, thank you very much. So if you're interested in any of the topics that I touched upon, I'll be happy to share information. Thank you very much. Should I just leave the Zoom?